per coulomb. Now, potential at a point in an electric field, we know delta V equal to negative E dr. That's what we obtained some time ago. Now consider 2 points A and B in the electric field produced by this charge Q. Now that's a charge Q, this is point A and this is point B. The electric field at a point distance r from a charge Q, alright, you can tell me that. What is the electric field at a point distance r from a charge Q? Will be kq over r squared. E equal to kq over r squared. Now that means delta V equal to, if you now apply that for point A, delta V equal to negative E, I'm going to replace E by kq by r squared times dr. Now A is at a distance r1 from the center of the charge. If this distance is r1 and B is at a distance r2 from the charge. Now what does delta V represent? Delta V represents the potential difference between the points A and B. The potential difference between the points A and B is negative E dr, where we assume that dr is so small that E will remain a constant. You see, in other words, A and B are very close together. The distance dr is so small that we will assume that the field in that region dr will remain a constant kq over r squared. The potential difference between A and B can now be obtained by integrating delta V. If you integrate now this delta V from r equal to r1 to r equal to r2, then we can obtain a measure of the potential difference between A and B. So VR2 minus VR1, what does that tell you? VR2 is the potential at a point distance r2 from the charge. VR1 is the potential at a point distance r1 from the charge. VR2 minus VR1 is a measure of the potential difference between the 2 points A and B, equal to integral r1 to r2 negative E dr, negative kq over r squared dr. Alright, now k is a constant, is that right? And q is a constant, we can take them out. So that will be kq times integral, well, let me write that step for you. That will be equal to kq times integral r1 to r2 negative 1 over r squared dr. Now, what is integral of negative 1 over r squared dr? Any elementary calculus student should know that. You know, what is the derivative of 1 over x with respect to x? You know that? The derivative of 1 over x with respect to x is negative 1 over x squared. Therefore, if you integrate negative 1 over x squared with respect to x, you should get 1 over x. In the same way, integral of negative 1 over r squared dr is 1 over r. So this will be equal to kq times 1 over r, and the lower limit is r1, the upper limit is r2. And what I have done in this step is write this with the kq inside. So integral r1 to r2 negative kq over r squared dr equal to kq over r from R1 to R2. Now we will replace this R by R2 for the upper limit minus replace R by R1 for the lower limit. So that will be KQ over R2 minus KQ over R1. And that is potential at a distance R2 minus potential at a distance R1. Now, suppose we choose R2 to be at infinite distance from the charge we have. Then, if you say R2 is infinite, and we say suppose the potential at infinity is 0. That means VR2 we are going to call 0. When that R2 is infinite distance from the charge, this VR2 will be 0. And also one more quantity on the right side will become 0. When R2 is infinity, KQ over R2, anything divided by infinity is 0. So look at the change we can make there. 0 minus VR1, negative VR1 equal to, when R2 is infinity, this quantity is 0. 0 minus KQ over R1 is negative KQ over R1. And what does that give you? If you now replace R1 by R, instead of calling the distance R1, we're going to say let the distance of the point be R, measured from where? Measured from the center of the charge. If you now replace this R1 by R and cancel the negative signs from both sides, we get VR, potential at a distance R from a charge Q, is KQ over R. Now look at that beautiful and very interesting, very important equation. The electric potential at a distance R from a charge Q is V equal to KQ over R. So take a note, make a note of that and keep it with you. Now this is a measure of the potential at a distance R from a charge Q. Now, one thing we must understand, if the potential due to a positive charge is a high potential, then the potential due to a negative charge will be a low potential. You see that? Remember the direction of motion of a positive charge. If you place a positive charge in this field, the direction of motion of the positive charge will be the direction of the electric field, which is the direction of decreasing potential. So the potential near a positively charged object is a high potential. The potential near a negatively charged object is a low potential. So a test charge, when placed in the electric field, will flow. Is it reasonable for me to say it flow? It will flow from a high potential to a low potential in the direction of decreasing potential, in the direction of the electric field. All those concepts are the same. Consider the electric field between a positive charge and a negative charge. The potential at a distance R from the positive charge will be positive KQ over R. The potential at this point due to this positive charge Q will be positive KQ over R. There you are. And if you now consider a point, now what is the potential at that point due to the negative charge? If you take a point here at a distance R from the negative charge, the potential due to the negative charge will be negative. You need to indicate that. So potential at this point due to the negative charge will be negative KQ over R. The potential due to a positive charge will be positive, high potential. Potential due to a negative charge will be a negative potential. Well, does it mean that the potential is a vector quantity? No, potential is a scalar quantity. While electric field is a vector quantity, potential is a scalar quantity. Potential at a point in an electric field is a measure of the work done in moving a unit test charge from infinity to that point. Now, you remember earlier on we defined the potential difference between 2 points is a measure of the work done in moving a unit test charge from one point to the other. And when one point is infinity, you can define the potential at this point as a measure of the work done in moving a unit test charge from infinity to that point. Now that is the physical meaning of potential at a point. Potential at a point in an electric field is a measure of the work done in moving a unit test charge from infinity to that point. It is the same as saying in a gravitational field, gravitational potential at this point is a measure of the work done per unit mass in lifting it through height h. In a similar way, the electric potential at a point is a measure of the work done in moving a unit test charge from infinity to that point. Since potential is the work done per unit charge, what is the unit for measuring potential? It is measured in joules per coulomb. Alright, I will be asking you this concept every now and then as we go on. Electric potential is a measure of the work done per unit charge. It is measured in joules per coulomb and it is called the volt. So what is the unit for measuring electric potential? Electric potential is measured in a unit called volt. And what is 1 volt equal to? 1 volt is 1 joule per coulomb. Suppose I say the electric potential at this point is 5 volt. What is the meaning? It means in order to move a unit test charge from infinity to this point, the work that needs to be done is 5 joules. 5 joules per coulomb. What is the meaning that the potential difference between 2 points is 5 volt? It means to move a unit test charge from one point to the other, you need to do an amount of work 5 joules per coulomb. Alright? So keep these ideas alive in your mind. Volt is joules per coulomb. Now look at the electric field. We can now obtain a unit for electric field from this. Well, potential difference is measured as joules per coulomb and electric field is delta V divided by delta R. So give me another unit for electric field. Well, when I ask you another unit, do you know one unit that we measure electric field already? Yes, electric field is a measure of, alright, it is Newton per coulomb, work done, the force per unit charge. Electric field is measured as the force per unit charge, Newton per coulomb. You can also measure electric field in delta V divided by delta R. Delta V, the potential difference, is measured in volt, and delta R, the distance, is measured in meter. Therefore, volt per meter is another unit of electric field. Alright, if I give you a 1 point extra credit, I want to see how many of you will want to attempt that. Is Newton per coulomb the same as volt per meter?